The sunlight on your skin isn't 8 minutes old, it's ancient, older than civilization. So how can something that always moves at the speed of light take tens of thousands of years to escape the sun? What is light even doing in there? You look up and you see a clean story, a glowing ball. It makes light, the light leaves. 8 minutes later it lands on your face, warms your skin, powers a leaf, hits your phone camera. End of story. That story is only half true. Yes, the sunlight hitting you right now took about 8 minutes to cross space. That part is fine. Space is mostly empty, and in empty space light really does move at the speed of light with nothing to slow it down. But the other half of the story, where that light came from and when it was born, is where your intuition quietly breaks. Because the sun is not a hollow lamp with a glowing surface. The sun is a deep ocean of plasma. 1,000,000 Earths could fit inside it. And the place where energy is actually produced, the core, is buried under an enormous weight of hot, dense material. If you could somehow stand at the sun's center, the pressure is so high that atoms are crushed into a soup of nuclei and electrons. And in that soup, nuclear fusion happens. Hydrogen nuclei slowly turn into helium, and the mass difference becomes energy. So far, still a neat story. Fusion makes energy. Energy becomes light. Light comes out. Now here's the problem we're going to take seriously. If energy in the core becomes a photon, if it literally becomes light, why doesn't it just shoot straight out at the speed of light? The sun's radius is about 700,000 kilometers. Light could cross that distance in a couple seconds. Even if you're sloppy, call it 3 seconds. So why are physicists comfortable saying that sunlight you're seeing is tens of thousands, even hundreds of thousands of years old? That sounds like a contradiction. Either light is fast or it's not. And we've all heard nothing is faster than light so many times that it feels like a law of existence, not just physics. So what is going on? The first thing to admit is that your mental picture of a photon traveling is probably wrong for this situation. You imagine a tiny bullet of light with a clear identity. It is created in the core. It keeps being the same photon, and it travels outward like a straight arrow. Inside the sun, there are no straight arrows. Inside the sun, there is barely even the concept of the same photon for very long, because the sun is not transparent, not even close. A photon inside the solar interior doesn't get a clean flight through empty space. It tries to move a tiny distance and then it hits something charged, mostly electrons, because electrons are everywhere in that plasma and they love to interact with light. The photon is absorbed or scattered, or it kicks an electron, or gets re-emitted. It changes direction, it changes energy, it stops being neatly trackable, and then it happens again, and again, and again, not 1,000,000 times, more like an absurd number of times. So the speed of light is not the right speed to use for the journey from the core to the surface. The photon is always moving at c* between asterisk interactions, but the mean free path, the average distance it can travel before something interrupts it, is incredibly small in the deep interior. Think of it like trying to run across a crowded room versus running across an empty field. In the empty field, your speed is your speed. In the crowded room, your maximum running speed doesn't matter because you collide with people every step. Your progress across the room becomes a slow wandering drift. You can sprint between shoulders, sure, but you're still trapped in the crowd. That's the sun's interior. A crowd of charges so dense that going straight isn't an option. So instead of a straight line trip, the energy performs a random walk. Random walk is a simple idea with a nasty consequence. Progress is painfully inefficient. If each step is random, forward and backward are equally likely. You might move outward a little, then back inward, then sideways, then outward again. And if your step size is tiny, getting a large net distance takes an enormous number of steps. That's why the number you hear is not seconds, but thousands of years. Now, to be honest, different models give different diffusion times. Depending on how you treat the changing density and opacity through the sun, you'll see estimates from roughly 10,000 years up to a few 100,000 years, sometimes even longer. But the core message is stable. It is not minutes. It is not days. It is geological in human terms. Which leads to a strange thought. When you see the sun shining, you are not seeing what the sun is doing now in its core. You're seeing what the sun's core was doing when humans were drawing on cave walls. You're seeing sunlight as a delayed message, a memory that had to fight its way out of a dense star. And that raises a second problem. If the photon is constantly being absorbed and re-emitted, is it even meaningful to call the sunlight that old? Is it the same photon? Or is it the same energy? Or neither? Good, that confusion is exactly the doorway into real understanding, because there are two different times in this story. One, the travel time through space once the photon escapes the surface, about 8 minutes to Earth. Two, the transport time inside the sun, the slow diffusion of energy outward through countless interactions. When people say sunlight is 100,000 years old, they're pointing at the second time. They're saying the energy that ends up as visible sunlight at the surface was generated in the core a very long time ago, and the interior of the sun is so opaque that energy takes ages to leak out. But we still have to be careful, because fusion does not usually produce visible photons directly. The core is unbelievably hot. The first radiation is typically high-energy gamma rays. As those gamma rays interact with the plasma, they get degraded, absorbed and re-emitted at lower energies, split into multiple photons, scattered in ways that shuffle energy around. By the time the energy reaches the sun's outer layers where photons can finally stream freely, the spectrum has been transformed into the sunlight you recognize, mostly visible and infrared. So the age is not the age of one heroic photon surviving intact for 100,000 years. It's the age of the energy packet, if you can even call it a packet, that slowly diffused outward, being broken, shared and reshaped until it finally escaped as many lower energy photons. That may sound like word games, but it matters, because it tells you what physics is really claiming. Physics is not telling a fairy tale about a single photon's epic journey. Physics is telling you something colder and weirder. In a dense star, radiation behaves like a trapped gas. It has a pressure. It carries energy. It diffuses the way perfume diffuses through a room, not by a straight shot, but by endless jostling. And if that idea feels slippery, that's because it attacks a hidden assumption that light always means fast signal, immediate output. Inside a star, light is not an immediate output. It's a delayed leak. Now here's the punch of the problem statement, the thing we need to resolve in the next parts. How can something that always moves at the universal speed limit still take 100,000 years to get out? What exactly is the photon doing in there? What are these collisions with light, and why do they trap it? And if photons are trapped for that long, why isn't everything trapped? Why does anything escape at all? There's also a final twist we'll keep on the table. The sun produces another kind of messenger from the core, neutrinos, that do not get trapped the same way. They pass straight through almost everything. So there exists right now a real-time signal from the sun's core arriving at Earth, but it's not light. So the situation is upside down from what you'd guess. The sunlight you see is ancient, and the now of the core is mostly invisible to your eyes. That's the problem. In the next part, we'll build the mechanism carefully, what the sun is made of, what opacity really means, what a mean free path is, and how a random walk turns the speed of light into a crawl without breaking any laws. So, let's build the trap without mysticism. Start with one blunt fact. The sun is made of charged stuff, mostly hydrogen and helium, but not as nice neutral atoms like in a balloon. In the deep interior, the temperature is so high that electrons are ripped off. You don't have atoms. You have a plasma, free electrons and bare nuclei flying around, constantly colliding. And light, an electromagnetic wave, a photon, whatever picture you like, talks to electric charge. That's what electromagnetism means. If there are charges everywhere, light cannot ignore them. That's opacity, not darkness, not fog in the everyday sense. Opacity is just how likely is a photon to get interrupted per centimeter. To make that precise, physicists use a clean idea, mean free path. Mean free path is the average distance a particle travels before it interacts. In air at room conditions, visible light has a huge mean free path, which is why you can see across a room. In the sun's interior, the mean free path is tiny. How tiny depends on depth, but deep down it can be millimeters, centimeters, sometimes less, not kilometers, not meters, little bytes. Now picture the geometry. The energy needs to travel about 700,000 kilometers outward. If each straight run is, say, 1 centimeter before something happens, the number of runs is not 700,000 kilometers divided by 1 centimeter. That would be the naive straight line number, but it's worse, because the direction gets randomized. This is the cruel math of a random walk. The net displacement grows like the square root of the number of steps. If each step has length L, and you take n random steps, your typical net distance is about L root n. You want that to equal the sun's radius r, so root n in sen r/L, meaning n sen r tway tree square. That's the killer. Put numbers in, roughly. R is about 710 cm. If L is 1 centimeter, then n is about 710 cm tway tree, 510 cm 21 steps. Now ask how long per step. Between steps the photon moves at c, about 310 cm. So 1 centimeter flight takes about 1/310 cm, roughly 310 cm 11s. Multiply 510 cm 21 steps, cross 310 cm 11s steps in 1, 510 cm 11s, and 1, 510 Cmen 11 seconds is about 5,000 years. That's with an optimistic 1 centimeter mean free path everywhere, which is not true. Deep inside it can be smaller, near the surface it gets larger. The sun's density changes by orders of magnitude. When you integrate through the actual structure, you can easily land in the tens of thousands to hundreds of thousands of years. But the point isn't the exact number, the point is the mechanism. The speed limit doesn't help when you're forced to take an astronomical number of tiny randomized steps. Now what are these steps physically? What does it mean for a photon to hit an electron? There are few processes, but you can keep the intuition simple. Sometimes a photon is scattered. It comes in, it interacts with an electron, and it leaves with roughly the same energy but a different direction. That's like billiards, except it's quantum and electromagnetic, and nobody's actually touching. But for direction, it's fine. Sometimes a photon is absorbed, meaning its energy goes into the motion of charged particles. The energy becomes heat, random jiggling of the plasma, and then that energy is re-emitted as new photons. Not necessarily one photon, could be several, not necessarily the same direction, definitely not the same identity. That's why tracking the photon is the wrong obsession. The interior is more like a bank account. Energy is deposited and withdrawn constantly in different denominations. So inside the sun, radiation and matter are coupled. They are exchanging energy all the time. The radiation field is in a kind of near thermal equilibrium with the hot plasma. That's a fancy way of saying photons are being created and destroyed so rapidly that the spectrum tends to match the local temperature, which is why the core produces mostly gamma rays and hard X-rays. High temperature means high energy photons are common. As energy moves outward to cooler regions, the typical photon energy drops. By the time you get near the surface, the temperature is around 5,800 K, and the radiation looks like what you call sunlight. So the sun is doing something subtle. It is converting nuclear energy into a thermal radiation field that slowly leaks outward. Leak. That word matters, because it implies containment. Why is it contained? Because the plasma is dense and charged, and electromagnetism is strong. Now there's a natural objection that smart people raise. Wait, if photons are constantly being absorbed, doesn't that mean the energy is basically moving as heat through the material? Why call it photons at all? Great. That's where the sun's internal structure matters. The sun has layers defined by the dominant transport mechanism. Deep inside, in the radiative zone, energy transport is primarily radiative diffusion. That means the energy is carried by photons, but in the random walk sense, photons are constantly interacting, but the main way energy moves outward is still through radiation propagating between interactions. Farther out, in the convective zone, the plasma becomes opaque enough and the temperature gradient steep enough that radiation isn't efficient. So the sun does something more dramatic. It moves hot material upward and cooler material downward. Convection. Like boiling water, but on a scale where the bubbles are the size of continents. In that convective zone, energy is carried largely by the bulk motion of matter. Photons are still there, still interacting, but the dominant outward transport is the physical movement of hot plasma rising. And then near the photosphere, the visible surface, the density finally drops so much that photons can travel long distances without being interrupted. That's where light finally decouples and streams away freely. So the slow part is mainly getting through the radiative zone by diffusion, and then the convective zone moves energy by stirring. The combined result is still that the energy is old when it escapes. Now let's do an even more brutal thought experiment, because it makes the trap feel real. Imagine you could shrink yourself down and place a tiny detector in the sun's core. You press a button. I create one extra photon right now. You might think, I'll see it exit the sun a little later, like a tracer die. No, you will not. That extra energy will be instantly shared among countless particles. The photon will not remain a clean, countable traveler. The extra will spread out, mix, thermalize. It will become a microscopic change in a huge sea of radiation and matter. The eventual effect at the surface is not a single bright dot that leaves later. It's an almost unmeasurable increase smeared over space and time. That is what diffusion does. It erases identities. So when we say the sunlight is 100,000 years old, we're speaking in the only sensible way. The energy you're receiving now was injected into the sun's interior long ago, and the sun's interior kept it trapped as part of its thermal radiation field for an enormous time before it leaked out. Now here's a second twist that makes the idea bite harder. The sun's luminosity, the power it outputs, is about 3 × 10^26 watts. That's ridiculous. but because the diffusion time is so long, the energy density stored inside the sun as radiation and heat is enormous. The sun is like a massive reservoir with a tiny outlet, which means if fusion in the core stopped today, just hypothetically, no physics explanation, just stopped, the sun would not go dark in 8 minutes. It wouldn't even go dark in 8 days. It would keep shining for a long time because you have a huge stored energy reservoir slowly leaking out. The surface doesn't instantly know what the core is doing. It is not directly connected by an immediate beam of light. It's connected by a slow diffusive pipeline. That alone should change how you picture a star. It's not an LED, it's not a flame, it's a slow thermal machine with delayed output. Now bring back the other messenger, neutrinos. In the core, fusion reactions produce neutrinos, and neutrinos interact so weakly with matter that the sun is basically transparent to them. Most neutrinos created in the core leave almost immediately and fly to Earth in about 8 minutes, like photons in empty space, except they don't care about the sun in between. So if you wanted a now report from the solar core, neutrinos are it. And the crazy thing is we detect them. It's hard, but it's real. Giant tanks of water deep underground, watching for a tiny flash when a rare neutrino interaction happens. And those detections are a direct confirmation that fusion is happening now. So you have two streams arriving at Earth. Light, the sun's delayed, processed ancient leak. Neutrinos, the sun's near real-time whisper from the center. Your eyes evolved to catch the ancient leak, not the whisper. Now one more subtlety before we move on, because it prevents a common misunderstanding. Nothing here says that an individual photon is literally moving slowly. Between interactions it moves at c always. The slowness is statistical. It's a property of transport in a medium. This is the same reason smell spreads slowly in a room, even though air molecules are moving at hundreds of meters per second. They're fast, but their direction changes constantly. Net progress is slow, so the sun has taken the fastest thing in the universe and forced it into the slowest possible kind of journey. A drunken stumble through an ocean of charge. That's the mechanism. Next, we need to connect it to something you can almost see, what surface means, why the photosphere is not a solid boundary, and how the idea of the age of light changes when the photon you receive is the end product of countless transformations. Because the sun isn't just delaying light, it's rewriting it. So what finally happens at the surface? First, kill the picture of a hard boundary. The sun does not have a solid shell. There is no place where you can put your foot. What we call the surface, the photosphere, is simply the layer where the sun becomes transparent enough that a photon has a decent chance of leaving without immediately being scattered back in. It's defined by an optical depth. Basically, from here, the odds of escape become reasonable. It's a statistical surface, like the surface of a fog bank. There isn't a wall, there's a region where the density drops and suddenly you can see out. Below the photosphere, photons are still trapped in the diffusion game. Above it, they're mostly free. Not perfectly, some scatter in the solar atmosphere, some get absorbed by atoms, you get spectral lines, all that beautiful structure, but the key transition is the photon can finally stream outward, and then 8 minutes later it can hit your retina. Now here's the mind-bending part that people don't say out loud enough. The photon that hits your eye was not the photon made in the core, it's the final receipt from a long chain of conversions. Deep down, fusion releases energy mostly as kinetic energy of particles and high-energy radiation. That energy gets shared, randomized, degraded, re-emitted. It becomes part of a thermal radiation field. It drifts outward for ages. Then near the photosphere, where the temperature is lower, the typical photon energy is lower. The sun emits a spectrum close to a blackbody at about 5,800 K, peaking in visible light with plenty of infrared. So the sunlight you see is basically the sun saying, here is the shape of my surface temperature. That's why when you measure sunlight, you can infer that temperature. It's not magic, it's thermal physics. But the deeper memory is not in the color. The memory is in the timing, in the delay. When you look at the sun, you are looking at a star that is slow to speak. A star is a giant conversation between the core and the surface, and photons are the messengers that keep getting intercepted, questioned, and sent back with edits. By the time the message finally leaves, it has been rewritten 1 trillion times. So is it meaningful to say sunlight is 100,000 years old? Yes, if you mean the energy budget. No, if you imagine a single identifiable photon with a birthday and a passport stamp at every layer. A better way to say it is this. The warmth on your face is energy that was released long ago in the sun's core, and the sun stored it and processed it and only now is letting a tiny fraction of that ancient energy escape. And that leads to an unsettling, almost personal conclusion. Everything you experience as now is delayed, not just because light takes time to travel through space, but because nature often stores energy in reservoirs and only releases it slowly. The sun is a reservoir. Your house's walls are a reservoir of heat. The ocean is a reservoir of summer. Even your brain is a reservoir. Memory is literally stored structure that takes energy to build and time to erase. The universe is full of slow leaks, and the sun is one of the biggest slow leaks you will ever meet. Now zoom out one more step because it gets even stranger. That 100,000 year delay means the sun has inertia, not mechanical inertia but thermal inertia. It has a kind of buffering against sudden changes in the core. The surface brightness you see is stabilized by the enormous stored energy in the interior. So the sun isn't flickering like a candle because the processes inside it don't instantly show up outside. The star is thick. It smooths its own behavior. That's why the sun can be steady for billions of years. But the idea also gives you a new way to picture time. We talk about light from distant stars as millions of years old. That's true in the travel through space sense. But with the sun you have a different kind of oldness. Not distance oldness, but struggle oldness, escape oldness. The sun is right next to you, and yet its light is ancient because it had to fight through its own body to be born into space. And once you really feel that, the phrase speed of light stops being a magical slogan. It becomes a local rule that can still lead to global slowness, fast steps, slow progress. Now to keep our feet on the ground, let's be honest about what we do and don't know in simple terms. We do know the sun's density and temperature profile pretty well, because helioseismology, studying how the sun vibrates, lets us infer its internal structure. We do know radiative transfer physics and opacities to a high degree. We can estimate diffusion times and they come out enormous, but pinning down a single number like exactly 100,000 years is not the point. The point is that it's ridiculously large compared to your intuition, and the larger point, almost philosophical but not hand-wavy, is what it means for causality in a real material world. You can't always point to an event and expect an immediate signal, even if the messenger moves at nature's top speed, because the messenger might be trapped in the medium. Reality has bottlenecks. Now, if you want one final image to carry with you, make it this. Imagine the sun as a city under blackout curtains. At the center there's a fireworks factory producing energy constantly. Every time a firework tries to leave, it hits a crowd, gets taken apart. The pieces get handed around, reassembled into smaller fireworks and thrown again, over and over. Eventually, after an absurd amount of shuffling, tiny sparks finally reach the edge of the city and escape into the night. Those escaping sparks are what you call sunlight. When they hit your skin, you are not touching the present moment of the core. You are touching the sun's delayed past. And now the weird human part. You can treat that as a fun fact. Or you can let it change the feeling of daylight, because it means your ordinary afternoon is linked to an ancient chain of events deep inside a star. It means the brightness in the sky is not just illumination, it's history. It's stored time, released slowly as warmth and color. And it also means something comforting. The sun is steady not because it is simple, but because it is slow. It has a huge thermal memory. If you want to understand the universe, not as a list of facts, but as a set of mechanisms you can actually picture, keep going with this kind of question. Not what is the definition, but why doesn't the obvious idea work? Because every time your intuition says it should be instant, physics calmly replies only in empty space, only in the ideal case. In the real world, everything has to get out through the crowd. If you want another mindbreaker like this one, pick one everyday statement you think you understand, like solids are solid, or nothing is empty, or time flows, and we'll take it apart the same way.